Thank you very much, and thank you all for attending today. It is an absolute joy to give a talk about astronomy anytime, but I particularly love the opportunity to speak to a room full of budding physicists and astronomers. So just by a show of hands, how many of you are thinking about studying astronomy or astrophysics at university? Excellent. And hopefully by the end of today, all of your hands will be up and I will have convinced all of you that it is absolutely the best career that's out there. Just across the street in the computer science department, in the coffee shop, there's a little sign that says, you can do anything, but not everything. Now, over there, it's referring to have a cup of coffee before you get started on your workday. But I think it's the best description of what a physics education can do for you. It really lays the groundwork for critical thinking and problem solving, and you can do many, many things with it, not just research. So I'm a prime example of that. I was straight as an arrow, went through school, did my PhD, and did a couple of years as a postdoctoral researcher in astronomy and astrophysics. Decided after all that time that maybe research was not the best career for me, and I switched to science communication and outreach, so much like Jacob, and did that for a number of years. In that, started advising students and learning about careers, and I'm now actually a careers consultant for the university, so I help students that study STEM, people that have done PhDs, maybe even postdocs, maybe have even been in research for years, how they can take those skills and apply it to the whole wide world. So hopefully, by the end of today, you'll kind of get an idea of all the different skills that you can develop as a physicist. But I want to tell you about the exciting science first, particularly as it is British Science Week this week. I'm going to dim the lights just to make the images better, but you have to promise me you won't fall asleep in the middle of the talk for me. The topic for today is brown dwarfs. Now, when you hear about astronomy, people tend to think about black holes, galaxies, cosmology, and really, really exciting things, exoplanets, but nobody's really heard of brown dwarfs. It's a very small slice of astronomy, and we're going to dig a little bit into what it is, but what you'll find is that when we talk about objects in astronomy, it's very hard to define them rigidly. We tend to use classifications, okay? And one of the most recent, well, not so recent for you guys, you were little, but in 2006, when we were discovering planets around other stars, we had to reconsider what we call a planet, and this led to the reclassification of Pluto. So when I was your age, there were 9 planets, now there are 8. Does that mean that anything about the physical properties of the planets has changed? No. It just means that we've reclassified how we think about them. So with the brown dwarf, we have a working definition. It's a low-mass object with star-like and planet-like properties, okay? Quite a broad definition. It tells us that it's a little bit like a planet. It's a little bit like a star. So where did these come from, and why do we even need to classify what they are? Well, just to give you a brief history, they were first theorized in the 1960s as planetars or substars. As our ability to observe stars in our nearby solar neighborhood increased, we were able to detect dimmer and dimmer stars. That now has evolved to also seeing planets around other stars. But it was thought that there might be a group of stars that exist but are just too dim for us to actually see. The actual name was coined by Jill Tarter in 1975, but it wasn't until the 1990s that we actually definitively recognized the first brown dwarf as being discovered. You may recognize the name of Jill Tarter. She's the one that was the scientist that was portrayed by Jodie Foster in the movie Contact. So quite a big name. So how on earth do we observe these, and what are we looking for when we're looking for brown dwarfs? To answer that, we need to actually step back and think about astronomy as a science full stop. Now, with the exception of man going to the moon and a few robotic missions that have kind of gone in our nearby solar system, everything we know about astronomy and astrophysics comes from light. And I really want you to think about that for a minute. That's incredible. So everything we know about where we are in our solar system, how we fit into our galaxy, how galaxies interact with one another, how black holes merge with one another, the large-scale structure of the universe, this is all from light, okay? So you'll probably all recognize this sort of diagram. It's the electromagnetic spectrum, and astronomers use the full range of the electromagnetic spectrum to do the science that they do. When we're thinking about observing brown dwarfs, they are dim stars. That was how they were defined. So we're really using things that are just beyond the red end of the visible spectrum. So looking at infrared signatures, often referred to as heat, right? So these are things that may not be emitting in the visible spectrum, but giving off a bit of heat. Now, why did we only discover them in the 1990s? There's some obvious technological reasons for that. So here's a diagram showing, again, the electromagnetic spectrum. You can see wavelength going from small to large across the x-axis. And for a long time, we could only see that narrow visible band that cuts through the atmosphere until in the 1960s we discovered, oh, radio waves you can actually observe because there's a massive gap. Our atmosphere is not blocking radio waves. But for everything else, our atmosphere does an amazing job of blocking that light. So that's really useful for things like X-rays. We don't want X-rays and gamma rays bombarding us. That's dangerous. Ultraviolet also can cause a lot of problems. But you'll see, even in the infrared, there's a lot of opacity or inability to see through the atmosphere. So the advent of the Hubble Space Telescope and other space telescopes really launched the era where we could find these kinds of objects. A few infrared observatories that you may have heard of, IRAS, I'm going to struggle to remember what it stands for. Infrared Astronomical Survey, I think is what the S is, was one of the first satellites that was launched that was looking specifically at infrared wavelengths, gave us a lot of instrumentation techniques, so the evolution of how you can actually detect infrared radiation came from that satellite. The Spitzer Space Telescope, so this was a sister telescope of the Hubble Space Telescope, was actually launched in, I think, the 2000s, but it is still up and running, just barely. It is one technological difficulty with infrared telescopes is that you actually have to keep the detectors cold. So you have to send up some sort of cryo material to keep the detectors cold, and when that runs out, it just runs out. And you think, well, that's counterintuitive because it's space, and space is really, really cold. But to get that perfect temperature to really be able to detect those wavelengths, you need that cryotechnology. But the most famous current infrared telescope is JWST, the James Webb Space Telescope, which was launched on Christmas Day just a few years ago, and is looking at really big cosmological questions, but the great thing about it is that the wavelengths that it is attuned to are exactly the wavelengths that we expect to have brown dwarfs also emitting at. So here's a snapshot of some of the first brown dwarfs that were recognized. So you can see that little red colored dot, that's a false color image. GD 165b was there. This is the discovery image from the Palomar Observatory of another early brown dwarf that was discovered in 1994. This was a bit of a tenuous discovery. You can see it's kind of very much melted into the noise of that image, but it was followed up a year later by the Hubble Space Telescope, and you can clearly see that that's a companion to this star. Okay? Now, I've described them as really dim, really warm, really hard to find. So why on earth was there even an interest in finding brown dwarfs? Why would we care about them? Well, you may have seen a pie chart like this that talks about what our universe is made of. So very little of our universe is actually made up of visible matter. So the table, us, the chairs, the auditorium, that's only less than 5% of the entire, what makes up the universe. The rest of it are these mysterious things called dark matter and dark energy. So dark matter is something that regular matter we know interacts with all of the different forces that we know. The dark comes just from the unknown. We don't really know exactly what it interacts with. But dark matter interacts with just gravity. So it's not sensitive to electromagnetic forces, but it is sensitive to gravity. And we don't know what it is. So in the early days when this structure of the universe was being detected, when things were being observed and not acting the way that we physically thought they might be acting, it was thought that maybe a lot of the dark matter is physical matter, visible matter that we can see, we just haven't detected it yet. So if there's an idea that there's lots of these low-mass brown dwarfs floating out there, then maybe that's something that, that would account for that quote-unquote dark matter. We now know that, as we've discovered them, that's not accounting for all the dark matter. So dark matter must be something that is a bit different. And I won't get into dark energy. That is a good topic for another day. But it is what I like to call the 21st century ether, something that governs how we see the universe, but it's not really very well understood. Another reason to study brown dwarfs is that they're some of our closest neighbors. As we've been discovering it, some of it is self-selective. So when we think about writing up the results of what we do, scientifically, we do have to think about, is there some bias in what we're thinking about? So when I say that some of our closest neighbors are brown dwarfs, there's a bias, because we're only going to see things that are close by to us. They're really dim. We're more likely to see it if it's close by. That being said, it is quite interesting because we are seeing things that are in our solar neighborhood. It tells us a little bit about our place in the galaxy and how we formed in relation to the stars around us. And most importantly, for me at least, and the focus of today's talk, is to look at why is a brown dwarf more like a star, or is it more like a planet? And what does that tell us about the relationship between a star and a planet? And a star and a planet are two of the most fundamental astronomical objects. They've been observed since antiquity. We have the sun and the stars out there. We have the planets. And for years, for centuries, we've been trying to understand, how do stars form, how do planets form, and how do stars and planets form together? And looking at brown dwarfs can really give us an idea of how those two objects are alike, how they're different, and how that affects their formation processes. But we don't have all the answers. At the end of the day, stars and planets are quite different. And brown dwarfs are a little bit like stars, a little bit like planets, but they're actually quite different from both. They have their own unique set of properties. So what we're going to do is we're going to look first at stars, have a bit of an understanding of the properties that are common to all stars, do the same for planets, and then figure out maybe where these brown dwarfs might fit in. And particularly, like I said, it can have understanding brown dwarfs and how they form and where they are and how they interact with both stars and planets tells us a lot about the formation processes between stars and planets and how they differ. So to do this, we're going to investigate some basic properties of astronomical objects, things like mass, temperature, radius, age, the presence or absence of companions. So did they form in isolation? Did they form next to something else? And the properties of the light that they emit. So again, looking at the full electromagnetic spectrum and using that to understand what the properties of these objects are. So we're going to start off with, what is a star? Does anyone want to venture a guess of what's a really simple one-line definition of a star?
A celestial body that contains energy in which nuclear fusion occurs?
Excellent. You hit the nail on the head. Nuclear fusion. What defines a star is the fact that it is something that is massive enough to squeeze two hydrogen atoms together in its core, and that allows it to emit light, and you've got a star. That's all it takes. You would think that they would be quite uniform if that's the defining characteristic, but stars actually come in many, many shapes and sizes. And confusingly, they don't all evolve in the same way. So you've probably seen this if you've taken an astronomy course, but all stars are born in stellar nebulas. But how they evolve is based on that initial mass that they have when hydrogen fusion starts. So when hydrogen fusion starts, if you have a low mass star like our sun, puny, low mass star, a million times the mass of the Earth, but still puny and low mass. It'll evolve eventually to a red giant star. Its outer layers will puff off and leave what we call a planetary nebula. And you'll get this remnant in the middle called a white dwarf. It's quite a passive process. There's no explosions. There's no massive boom. It's a quiet, slow death, and our sun is going to be shining here for another 5 billion years before it gets anywhere near this stage. If you have something more massive than our sun, quite a bit more massive, at least 10 times, maybe 50 times more massive than our sun, it's going to follow a very different path. So these stars are hotter, bluer stars are hotter. They puff up into a giant, but they have more energy in their core that allows them to fuse heavier and heavier elements. So they're going to fuse hydrogen into helium, they're going to fuse helium into carbon, and they're going to keep going until they get to iron. And when they try to fuse iron and iron together, guess what happens? You don't have enough energy to do that, and it explodes in a runaway reaction called a supernova. Now, that is violent, it is spectacular, it happens instantaneously, and we can observe that, and it's really, really interesting. And you end up with either a neutron star, you may have heard of a pulsar, which is just a rotating neutron star, or the ever-famous black holes. So really small, really dense cores, okay? A white dwarf has the mass of its star in the size of a planet. So when the sun goes through this process, it will end up occupying a space the size of the Earth, but with the mass of the sun. A neutron star does the same, but it'll be the size of a city. And a black hole does it, but it's a singular point. And I'm not going to get into those mathematics, but they're very, very interesting. So where do brown dwarfs fall along this line? How do they form and how do we see them? So if we look at a snapshot of star formation, and this is particularly looking at low mass star formation because that's what we are interested in with brown dwarfs, is you start with a big ball of gas and dust. At some point you have enough stuff in enough area, it's called the Jeans radius or the Jeans mass, and it allows it to gravitationally fall in on itself. And you end up with a spinning thing that flattens into a disk. That's using angular momentum. It's the same thing that happens when you're spinning pizza dough and it flattens out. Eventually, the bits of that disk clump together, usually more in the center and bits outside, and you get this lovely solar system with a big hunk of gas in the middle, the star, surrounded by the planets that went around it. This is pretty well accepted as low-mass star formation. We have actual observations of this process. So this is a snapshot of the Orion Nebula from the Hubble Space Telescope. And you can see we can actually catch glimpses of what star formation looks like in those very early stages, where you start to see that bright star in the middle in that envelope. And there's even pictures where you can start to see that dusty disk formation happening. So that's pretty well understood, pretty well accepted by the astronomical community. At some point when that has accreted enough into its core, it has that ability to start fusing hydrogen into helium, and that's what we call the beginning of a star's life cycle. It's turning into a star, it's shining. And you may remember from your basic physics classes that heat can be transferred in a number of different ways. And in a star, we actually see different ways to transfer heat. So in the core, photons are produced from the nuclear fusion, and they're radiated out. But if they had to radiate all the way out to the surface, it would take millions and millions of years for that energy to get out. And a lot of it would be absorbed along the way. So in stars, we actually have a radiative zone in the center, but then we have a convective zone that carries that energy to the surface much, much more quickly. And that's really cool because that allows that energy to move to the surface very quickly and allows it to radiate out. So very important for us. We wouldn't have the heat that we need on Earth if we didn't have that convective process. Again, it's pretty well understood. This is a very, very zoomed in image of the surface of the sun from one of the probes that orbits the sun. And it was taken in 2019. And each of these little pockets are convective cells. So if you think of a pot of soup bubbling, you've got the energy bubbling up to the surface of the sun. And it's actually really, really cool. You can see that convection happening on the sun. Now, we don't actually see that on brown dwarfs, but what we do see is that we can do a bit of physics and find out that they are fully convective. So that makes them extremely star-like. So a star like our sun, it has a radiative core and then has convection that pulls the energy to the surface. As we get to lower and lower mass stars, you will see that a lot of them are fully convective, so that energy is formed, but it doesn't radiate outward. It actually just carries, depending on the composition of the outer layers of the atmosphere. So in brown dwarfs, we found that they are fully convective, which makes us think that they're very much more similar to a star because you have energy being formed in the center. Now, I did ask, what is a star and how do we define a star? And that's very much about that ignition of nuclear fusion. Now, what's interesting about a brown dwarf and what makes it very different from a star is that they don't quite ever get hot enough to fuse hydrogen into helium. So if you remember that brief history that I gave you, when they were first theorized, it was actually stemming from this. It was stemming from the idea that maybe we have objects that are failed stars. They get close enough, we think that they're big enough to be able to fuse hydrogen, but they don't actually get to that point. Now, the eagle-eyed among you might be saying, but then how do they shine? How do we see them? How are they emitting any radiation at all? And it's very, very weird. So what's happening in a brown dwarf is that you don't have the nuclear fusion in the core, but you may have a little bit of fusion of other isotopes of hydrogen. So something called deuterium could be fusing in the core. But what's really making it shine is the force of gravity pulling down. And at some point, that gravity is balanced by electron degeneracy pressure. Okay? So electron degeneracy pressure is kind of a weird concept, but if you remember your orbital chemistry, you know that electrons like to be they like to keep their space. A really good analogy that I once heard was, imagine that you are getting onto a subway train really late at night and everyone's packing in, and at some point, everyone locks their elbows out and says, no more, no one else can fit in this carriage. That's exactly what's happening with electron degeneracy pressure. The electrons are coming together and saying, this is it. This is all that we can pack in, and that provides that external force. Now, in a star that is fusing hydrogen, you also have an external pressure, but that's what we call radiation pressure that's coming from the fusion. And that's balancing, that's preventing it from falling in on itself. So you have the radiation pressure and the gravity perfectly balancing one another in what we call hydrostatic equilibrium. You have a similar sort of balance in a brown dwarf, but it's not caused by that radiation pressure. It's caused by electron degeneracy pressure. What that means, though, is that brown dwarfs do shine, but they slowly get dimmer over time because there's nothing renewing that shine. It's from the gravitational infall. So this poses a problem because if we're looking to discover brown dwarfs, they're shining, but they're getting dimmer and dimmer over time. And so as a brown dwarf cools, it becomes harder and harder to detect. And we'll talk a little bit about how we can classify that as well. So it's a little bit like a star in that it may form like a star. It's a little bit not like a star because it's not fusing hydrogen in its center. What about the environment that it's in? Some of you might recognize, these are both illustrations. You might recognize this from Star Wars. On Tatooine, we've got twin stars, a binary star system. This is an illustration of a binary star system. We tend to think of binary star systems as very exotic, But actually, nearly 70% of all stars are in binary systems or multiple systems. So sometimes you'll have 3 or 4 stars together. Our sun is a bit of an anomaly in the sense that it's isolated and it's a single star in the solar system. So when we are looking at binary systems of stars and brown dwarfs, many of them have been found in binary systems. So this again leads us to think that maybe they form like stars because we see them in dynamic relationships with other brown dwarfs or with a young star. And you can see the two of them together. What about star disk systems? So again, looking at really young objects, when you have the star forming, the planets forming, and you have this star disk system together. This has also been observed. This is an example of a brown dwarf system, OTS 44. So here we have an illustration of our solar system, the planets sticking out. We've got a brown dwarf and little tiny planets orbiting around the brown dwarf. Now, if you have planets orbiting something, to me that sounds extremely star-like rather than planet-like. And there is very concrete data to show this. This is what we call a spectral energy distribution. It's just showing what light is being emitted from a star at different wavelengths. And this bottom part of the curve can be very easily modeled just by looking at a star of a certain temperature. You can look at that curve and say, I expect this star to be emitting. Where it peaks tells us what color it is, but what's all this fuzzy stuff coming off of it? So that's what we call an excess, in particular an infrared excess. So that excess emission, we know that the star itself is giving off the curve. That excess emission is coming from the heated dust around the star. So that little wiggle there is evidence of a disk around a star. What's happening is all the little particles are surrounding that star, tiny dust particles, are absorbing that radiation and re-radiating it in the infrared. It's literally heating up. And because this is early in the star and planet formation process, the particles are really, really tiny. They're not really big enough. They've got a lot of surface area, and that allows them to re-radiate almost to the amount that the star is radiating at any given wavelength. So this is the theoretical idea of what a disk around a brown dwarf might look like. And this is actual data. So the data point was taken from individual observations at those different wavelengths. But you can see that it very clearly shows that we've got that infrared excess. And this is just one example, but there's many, many examples of brown dwarfs that have been observed with disks around them due to that infrared radiation. So I think that there's a lot of star-like evidence. The formation processes are quite similar. They're able to burn deuterium, even though they can't burn hydrogen. We've observed that some of them are fully convective. They can be found as isolated systems, so you can have that star, or that brown dwarf on its own, and they can also host their own planetary systems. So I've never heard of a planet hosting a bunch of planets, but a star hosting a planet I can take. Now, hopefully I convinced you that they're very much like stars, but let's flip it the other way and think about planets and think about how we define planets and whether they're planet-like. So the word planet actually means wanderer. It comes from the Greek word meaning to wander, and it originally just defined the planets that we see in our solar system that have been observed since antiquity. So all of the planets, the rocky planets, plus Jupiter and Saturn, Uranus and Neptune were discovered later on. A planet today is defined by 3 particular characteristics. It has to orbit around the sun, so exoplanets are excluded from that because they're not orbiting around the sun. They have to have sufficient mass to be formed into a nearly round shape, and they have to have cleared their orbit from other orbits. So, as I mentioned, in our own solar system, we've discovered many, many more objects, causing us to reclassify Pluto and some of the other outer solar system planets as dwarf planets. Now, our detection techniques for finding objects has increased exponentially. So exoplanets is another thing that was theoretical in the 90s, and now we know we have actively observed more than 6,000 exoplanets, okay? So in order to do this, there have been a number of missions that have allowed us to do this. So this is an image of the WISE satellite. And again, it was looking at relatively cold wavelengths, so beyond the red end of the spectrum. And it really launched an era of finding many, many brown dwarfs, and many, many cool brown dwarfs. So remember that I said that brown dwarfs shine, but then they do cool off over time. So this was an opportunity to detect really, really cool temperature brown dwarfs. So here's an image from some of the data from WISE, and it is overlaid with objects that were detected previously, and it turns out that actually this blob is a binary system of brown dwarfs. There have been hundreds of brown dwarfs that have been discovered by this WISE mission. These cool brown dwarfs are quite interesting because they start to have us think about how planets are formed. And there's two major planet formation theories. One is the one that I alluded to before, that you've got a central star, you've got these dust grains. As they spin around, they clump together, and those clumps clump together more until you have a rocky core that makes something like the Earth, or you have a really big rocky and icy core that can also hold on to gas that makes something like Jupiter. Now, as we've discovered more and more planets, what we found is that this theory doesn't necessarily work very well, because we found in order for big gassy planets to form, they need to be far enough from their central star to have ice in their core. That's what makes them massive enough to hold on to the gas. You can't do that with something like the Earth. It's not massive enough to hold on to that atmosphere of gas. So the first exoplanets that were discovered were found very, very close into their host stars. And we had to come up with another theory to account for this. And so this is called the gas instability theory. And basically what it says is you have a protostar forming in the center, but as that gas and dust is swirling around, you have some other forces acting on it, and that's causing the gas to swirl such that that gas giant planet is formed simultaneously with the proto-sun. Now, that's really interesting because that could be also a formation technique that works for our solar system, right? We could have the sun and Jupiter forming together. It could work for a star and a brown dwarf. It could even potentially be the formation for binary star systems. So when we're looking at brown dwarfs, if we think about this other theory of planet formation, well, maybe they're more like super Jupiters. Where do they fall in the mass range? They're very low mass stars, but Jupiter is 1/1000th of the mass of the sun. Maybe brown dwarfs are just really, really, really low mass stars that are falling into that range of planets. We've also seen that now you can use spectroscopy to actually figure out the elemental composition of brown dwarfs, and they have really interesting clouds, things that we actually have only ever seen in other planets. We don't tend to think of weather or complex molecules as things that we see in stars. Stars are 99.99% hydrogen. Why are we seeing all of this other stuff? Where is it coming from? It's more likely that maybe those things are coming from the planet formation process. We've also actively observed banded structure. So these aren't photographs, but these are images that are created from real data of one of the systems that I showed before. And you can see that there's patches that are visible that are showing very different molecular signatures on the surfaces of these brown dwarfs. So there's a fair amount of evidence that they're planet-like as well. They've got the banded cloud structure. There's elemental composition that you wouldn't expect to see in a star, and they're found in orbit around stars. So this gravitational instability theory says, okay, yes, we see brown dwarfs that have planets around them, but we also see brown dwarfs that are going around stars. So are they more like stars or are they more like planets? It really depends. Regardless, I think they're fascinating objects, and they're ones that we can classify based on their other characteristics. So in some ways, it doesn't really matter whether we put them in the star bucket or we put them in the planet bucket. What we found is that they're unique enough as a class that we can classify them using some of the techniques that astronomers use to classify objects. So I'm sure many of you are familiar, if you've taken an astronomy class, with this classification scheme. So back in the 1900s, there were catalogs of stars where the observatory in Harvard in the US was looking at the spectra from different stars, and they noticed different patterns, that certain elements were absorbed quite distinctly, and you could kind of group stars together. And originally it was an alphabetic classification, A stars, B stars, etc. As we learned more about how stars evolve, what temperatures they are, and all of that sort of thing, we reshuffled this so that it's OBAF, etc. And that correlated better with the physical properties of the stars and how they evolve. So with brown dwarfs, if you actually look at the spectra, you start to see really interesting characteristics, and you start to see patterns. So this is looking at the same thing. It's showing you the spectra, but we've just plotted intensity against wavelengths. So at a particular wavelength, you can see how strong the emission is. And you can see here, well, hopefully you can see it says M, M, L, 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 and all the way down to T. And there's enough differences in the spectral characteristics of brown dwarfs to be able to use the spectral typing that we use for stars for brown dwarfs, which is really, really fascinating, because that starts to tell us that, okay, the ones that are more like stars, maybe more massive, maybe a bit hotter, maybe able to burn deuterium, we're gonna call them L dwarfs because they're more similar to M, the really low mass stars. And the ones that are getting more planet-like that we're discovering with some of those missions that are focused more on finding the really cool brown dwarfs are going to be Y dwarfs, okay? And this is getting, that banded structure getting more similar to Jupiter. Now, I don't know if they still teach this. When I was in school, there was a mnemonic to remember this that said, "Oh, be a fine girl, kiss me." Now, I think it's 2026. That's a bit outdated. But how on earth do we add L, T, and Y onto that? Well, Andrew West, who is a professor at Boston University in the US, came up with that, and he said, "Oh, be a fine girl, kiss me," like that. Yeah. And now you will never forget it either. It's a completely ridiculous mnemonic, but it'll help you to remember those spectral types. I want to wrap up just with a couple of really interesting discoveries that have come from JWST. Sorry, that looks really dim. As I mentioned, JWST, its science mission is focused on cosmology and really large-scale structure, but luckily for the small slice of astronomers that look at brown dwarfs, it also looks at those really cool wavelengths that we see when we're looking for L, T, and Y dwarfs. So there have been some interesting discoveries, and they're continuing to be interesting discoveries as we get more and more data. So one is this, which is the tiniest free-floating brown dwarf discovered to date. So again, you can see this is actual images. The colors are not real because this is infrared data, but there were actually 4 free-floating brown dwarfs found in this nebulous region. Again, they were observed, their properties were measured, and we were able to classify them by their properties to be brown dwarfs. They're free-floating, so does that make them more star-like or more planet-like? This is evidence, again, leaning towards that star-like evidence. It's telling us that they're probably formed in isolation. They're probably free-floating. Another interesting result is that we can see aurora on brown dwarfs. Now, this is really, really bizarre because aurora, at least as we understand them in our own solar system, is happening because we've got particles from the sun hitting the planets. There's something irradiating it. But this aurora was actually, it was a study that looked at 12 different cold brown dwarfs. Okay, so we're looking at the L and the Y. And they were isolated. They weren't near enough to a star for something to trigger that aurora. And yet there were observations that implied that there were highly energetic activities happening on these brown dwarfs. So the reason I point out these two is that every day we're getting more and more data about brown dwarfs, more and more evidence about them, and we're still learning the best way to classify them, learning the best way to understand how to understand their formation processes. They're really interesting because they are everywhere. This is our sun, and you can see the reddish circles. It's not very visible on there. Are all brown dwarfs that have been found in our solar neighborhood. So they are very interesting. They're quite ubiquitous. Not enough to explain away dark matter, but they are something that are really interesting to see. If you're interested, there are some citizen science projects that you can do. I'm happy to send this link around maybe. That lets you look for brown dwarfs and other very dim objects combing through all of this data. So with that, I am going to stop and open it up to questions. Thank you very much.